Welcome to the Deep Dive. We're jumping straight into one of the bedrock theories of physics today, thermodynamics. The study of energy in its many forms, particularly heat and work. Einstein famously said that it's the only physical theory that, well, within its framework, will never be overthrown. Pretty fundamental stuff, right?
Absolutely. It's incredibly robust. Its principles are just so far-reaching. And today, we're not just talking concepts.
No.
We're really putting on our mathematical hats. We're going to meticulously go through the steps, derive some key equations.
Exactly. The goal is a real nuts and bolts understanding of why these equations look the way they do.
Why they work.
Right. We've got a detailed set of notes here, and our aim is to unpack the mathematical underpinnings.
Yeah.
And right off the bat, we hit this really useful distinction: d-coordinates and h-coordinates.
Ah, yeah.
Now, these might sound a bit abstract at first, but understanding them is crucial for defining what we even mean by a thermodynamic system.
Cool.
Think of d-coordinates as describing the system's mechanical deformation, its shape and size, like volume.
The physical form.
And we have h-coordinates, which tell us about the non-mechanical equilibrium properties, like pressure and temperature.
Right.
This D versus H idea is going to be a recurring theme as we go deeper.
It's a fundamental way to categorize the variables we use. I mean, think about a purely mechanical system, maybe like those particles connected by springs on a table.
Okay.
To fully describe its equilibrium, you only need the d-coordinates, the positions of the particles. Any change is just, well, a shift in their spatial configuration.
Makes sense.
Now, contrast that with our classic thermodynamic example, a gas trapped in a cylinder with a piston.
Right.
We can change its volume, sure, that's a d-coordinate. But we intuitively know volume alone doesn't define everything, does it?
No, definitely not.
The gas could be at high pressure, high temp, low temp, all for the same volume.
Exactly. That's where h-coordinates come in, right? They capture that internal equilibrium state beyond just the mechanics.
Precisely. And what's fascinating here, what our notes point out, is that a mechanical system only needs d-coordinates. But a thermodynamic system, crucially, requires at least one h-coordinate.
Right. You could have that same volume of gas, scorching hot or ice cold. A d-coordinate alone doesn't tell you that crucial difference.
Exactly.
So d-coordinates describe the system's outside, its physical form, while h-coordinates give us insight into its inside, its internal equilibrium.
Well put.
And here's a key point from our notes. D-coordinates are directly linked to work done by the system through mechanical changes. You move the piston, work is done.
Yep.
But h-coordinates like pressure or temperature don't have that direct work relationship.
Precisely. And that distinction leads us straight to the formal definition of a thermodynamic system.
Oh.
It's a system whose equilibrium states can be specified by a finite number of coordinates, with the essential condition that at least one of these must be an h-coordinate.
Finite number. That seems important.
It is, and it might seem like a straightforward definition, but it has a profound implication.
Which is?
For a system to be considered thermodynamic within this framework, its properties at a given moment should only depend on its current coordinates, not on its past history.
Ah, okay.
If the history mattered, you'd need like an infinite number of variables to describe it. But our definition limits us to a manageable finite set.
So, no systems with a memory then, just the present state captured by our finite coordinates. Let's quickly recap. Mechanical system, all d-coordinates, like the connected particles.
Right.
Thermodynamic system needs at least one h-coordinate, maybe some d-coordinates too, like our gas in the cylinder.
Got it.
Okay, so we have a handle on what a thermodynamic system is formally. Our notes then introduce the concept of a standard thermodynamic system. What makes a system standard for our mathematical explorations?
Good question. A standard thermodynamic system is basically a simplified model. It lets us derive fundamental thermodynamic relationships more easily. It's defined by a few key criteria.
Like what?
First, it has n coordinates in total, with exactly one h-coordinate and n1 d-coordinates.
One h and one d's. Okay.
Second, we assume that things like surface tension and long-range interactions like gravity are negligible.
Reasonable for many lab-scale systems.
Usually, yeah. For most macroscopic systems, these effects are indeed pretty small compared to the short-range molecular forces. And third, and this is mathematically very important, the work done by the system during an infinitesimally small deformation is linear in the changes of the d-coordinates.
Okay, linear dependence.
Expressed as w ports. Here, w atobU is the tiny bit of work, are the tiny changes in the d-coordinates.
And pk.
pk are the generalized forces corresponding to each d-coordinate. And these generalized forces, pk, are considered to be functions of the system's coordinates themselves.
So our reliable gas in a piston cylinder fits this bill, right?
Mm-hmm.
Volume V is our single d-coordinate.
Yep.
Pressure P is our h-coordinate.
Correct.
And the work done during a tiny volume change dV is WW, that's PdV.
Exactly. The negative sign there indicating work done by the system when the volume increases.
Got it.
Yeah.
And the notes do mention non-standard systems briefly.
Yeah.
What are some examples where these simplifying assumptions don't hold?
Right. Systems that don't meet these criteria are non-standard. Think multi-component systems, like mixtures of gases or solutions. They need more coordinates to describe composition.
Right.
Or systems where long-range forces are significant, like a star where gravity is dominant. That wouldn't be standard.
Right. Gravity is a big one there.
Definitely. Similarly, very small systems where surface tension becomes important, like nanoparticles or systems involving, say, external fields that can do work beyond just mechanical expansion, like a magnetic material in a magnetic field.
Those would all be non-standard.
They would, and they often require more complex mathematical treatments.
Okay, that clarifies why we start with these standard systems. They give us a manageable framework to build our understanding.
Exactly. Build the foundation first.
Now, once we have our D and H coordinates defined, we can define the state of a thermodynamic system. What exactly constitutes a thermodynamic state from a mathematical perspective?
A thermodynamic state, often denoted by sus, like the Greek letter.
Sigma.
Right, sigma. It's defined by a specific unique set of values for all the coordinates of the system. But, and this is crucial, as our notes emphasize, H-coordinates are only well-defined when the system is in equilibrium.
Only at equilibrium.
Yes. If a system, like a fluid, is undergoing rapid turbulent changes, you can't assign a single uniform pressure or temperature throughout it.
Makes sense. It's all over the place.
Right. Therefore, the concept of a non-equilibrium state isn't really well defined within this framework of classical thermodynamics. For us to make quantitative statements and predictions, the system must be in a well-defined equilibrium state characterized by that fixed set of coordinates.
So equilibrium is the fundamental prerequisite for a system to have a state that we can describe mathematically.
You got it.
And within these equilibrium states, we have these generalized forces, pk. How do they relate to the work done in these states?
Well, in a quasi-static process, that's an idealized process, where changes happen so slowly that the system basically stays infinitesimally close to equilibrium the whole time.
Super slow changes.
Right. In that case, the infinitesimal work done is given by that equation again, pi a w e's Pasc. Here, pk is the generalized force that is a conjugate to the d-coordinate x.
Conjugate.
Yeah, it's the force associated with that particular deformation. For our gas in a cylinder with a volume v as the d-coordinate, the generalized force pk is actually PA, the pressure.
Minus P. Why the minus again?
The negative sign arises because an increase in volume, positive dV by the system, results in work done by the system. This often means energy leaving the system, hence the negative pressure term in that convention.
Okay, work done by the system.
And the notes highlight a crucial point. These generalized forces, pk, are state functions.
State functions, meaning?
Meaning their values depend only on the current state of the system defined by all its coordinates and not on the path the system took to reach that state.
Path independence. Got it. All right, we're laying a solid foundation here. Let's move towards some more advanced mathematical tools. Free energy and the concept of homogeneous functions.
Okay.
Our notes briefly mention total density and partial molar volume for mixtures, but then quickly introduce free energy, F, as a first-order homogeneous function in Ni, the number of moles of each component.
Okay, let's break this down. What exactly is a homogeneous function, mathematically speaking?
Right. Mathematically, a function fx1 by 2 xn is homogeneous of degree k if, when you multiply each of its arguments by some scaling factor,
lambda.
the function itself gets multiplied by fs to the power of k.
Okay.
So the equation is ff1 by 2 if s can equal ff1 by 2 xn.
And the notes have examples. They do, like fxy equals x plus y, that's homogeneous of degree 1, because x plus y,
Simple, no?
and f(x,y), that's degree 2, plus f plus y s y plus y. Okay, I see the pattern. Why is this property important in thermodynamics?
It's super important because extensive properties, those that depend on the amount of matter in the system, exhibit exactly this scaling behavior.
Extensive property scale with thighs.
Exactly. If you double the size of a system, keeping intensive properties like temperature and pressure constant,
Right.
what happens?
You double the volume, double the internal energy.
Double the Gibbs free energy, right? This direct proportionality with the amount of matter means these extensive properties are first-order homogeneous functions, degree K, with respect to the number of moles of each component.
That scaling with the amount of stuff makes intuitive sense for extensive properties like VUG. So if we take Gibbs free energy G for a mixture, how does its first-order homogeneity in the number of moles play out mathematically? Okay, so Gibbs free energy G is a function of temperature T, pressure P, and the moles of each component N1, N2, Nm.
Right.
Its first-order homogeneity in the n variables means that if we scale the number of moles of each component by a factor while keeping T and P constant,
The K and P fixed.
then the Gibbs free energy G also scales by the same factors. So GTP N1 ln NOE is opal GTP N1 N2 Nm.
And T and P don't get the O because they're intensive.
Exactly. They don't depend on the amount of substance. This property is absolutely fundamental for understanding the thermodynamics of mixtures.
Okay, that link between extensive properties and homogeneous functions of degree 1 is becoming clear. Now, how does this property lead us to Euler's theorem? Our notes introduce that next as a key mathematical result for these functions.
Right, Euler's theorem. It provides a really powerful connection between a homogeneous function and its partial derivative.
Okay.
It states that if a function fx1 by 2xn is homogeneous of degree k, then the sum a of each variable of k multiplied by the partial derivative of f with respect to that coffin.
So C times Ursa summed up.
Exactly. That sum equals k times the function itself, from I1 to n, x by f by 1, xn.
And the notes show how to derive this.
Yeah, it comes directly from the definition of homogeneity.
Yeah.
You start with f1 xn, sf by 1 xn, then you differentiate both sides with respect to
That's with respect to the scaling.
Right. Using the chain rule on the left side gives elixir. The right side derivative is kk1 f by 1 xn.
Okay.
Now here's the neat trick. Sit lixi1, then xe just becomes xn, and I k1 becomes 1k1 x1, and boom, you're left with x tails. F by 1 xn. Euler's theorem.
That's a very elegant mathematical result. It just falls out from the definition.
Yeah.
So let's apply it. If we apply Euler's theorem to our first-order homogeneous Gibbs free energy, so K1, and our variables are the moles, what specific thermodynamic insight do we gain?
Okay, for a first-order homogeneous function, K1, Euler's theorem simplifies nicely to or n equals G or no equals G.
Sum of n times partial G partial n equals G.
Right. And crucially, the partial derivative, Arrhenius, is taken while holding T, P, and all other mole numbers, Nj where edges I, constant.
Got it.
Now, this specific partial derivative at constant T, P, and other Nj, this has a very important physical meaning in thermodynamics.
I feel like I know where this is going.
It's defined as the chemical potential of component I, denoted by I.
No, I. There it is.
So applying Euler's theorem to the Gibbs free energy gives us this fundamental relation. G equals I.
Wow.
This equation tells us the total Gibbs free energy of a mixture is just the sum of the chemical potential of each component multiplied by how many moles of that component you have.
That's huge. It connects the macroscopic G with this sort of microscopic-like property.
Yeah, exactly. It links the contribution of each species to the mixture's overall free energy.
Chemical potential, again, it seems to pop up everywhere in thermodynamics. So this powerful concept arises quite naturally from homogeneity and Euler's theorem applied to Gibbs free energy. Now, our notes then state that the chemical potential E itself is a zeroth order homogeneous function. What does that imply? How does I behave when we change the system size?
Right. So if G is first order homogeneous in moles, then its partial derivative with respect to any I, which is I, turns out to be a zeroth order homogeneous function.
Zeroth order, K0.
Meaning F1 cranks n, xn equals fx1 xn. The function doesn't change when you scale the arguments.
So I doesn't change.
Exactly. Applying this to chemical potential, ITP P NBP on M equals ITP N1 NM. If you scale the amount of all components in the mixture by the same factor, keeping T and P constant, the chemical potential of each individual component remains unchanged.
So it doesn't depend on the total amount, just the relative amounts.
Precisely. It depends on the composition, not the overall size.
So it's all about the proportions, the mole fractions. Our notes then define total moles N equals Ni and mole fraction Kg equals Ni Nang.
Kai.
And they say AE can be expressed as ITP P P P PG. That makes perfect sense if it only depends on relative amounts.
Exactly. The chemical potential is indeed a function of the composition, typically expressed in terms of mole fractions at a given T and P. And the notes rightly emphasize something important.
What's that?
I is not linearly dependent on the composition.
Right, not just proportional to the mole fraction.
No. Scaling all components by I scales the total Gibbs free energy G by high, sure, but it doesn't directly scale the individual ions. The relationship is more complex, often involving logarithms, as we'll see with ideal mixtures.
Okay.
Understanding this dependence on composition is key to deriving the fundamental thermodynamic relation for the differential of Gibbs free energy, dG plus VdP plus iodine.
The fundamental equation.
Yes. And notice, at constant temperature and pressure, dT equals 0, dP equals 0, this simplifies to dG at constant TP equals actually iodine. This shows how changes in Gibbs free energy are related to changes in the amounts of each component through their chemical potentials.
And from this fundamental relation for dG, we can derive the Gibbs-Duhem equation, which always seemed a bit abstract to me. Can you walk us through the derivation and highlight its physical significance?
Absolutely. The Gibbs-Duhem equation, which is any dD is 0 at constant T and P.
Sum of moles times change in chemical potential is 0.
Right. It's a crucial constraint that arises because G is both extensive, GHESAHINI, and its differential is dG equal SDT plus VdP plus ID.
Okay, how do we get there?
Start with dG and dt and take the total differential of both sides. Using the product rule on the sum gives dG equal I plus I and dN,
Okay.
which we can split into two sums, dG equal I and dN.
Right.
But we also know the fundamental relation, dG equals IdSdt plus VdP plus ani dN.
Okay, so we have two expressions for dG.
Exactly. Since they both equal dG, we can set them equal to each other. Mani dN plus mani SDT plus VdP plus mini dd.
Ah, and the anti-needy terms are on both sides.
Precisely. They cancel out,
Leaving
mi dd equal STT plus VdP.
Nice.
Now, if we consider a system at constant temperature and pressure, so dT equals 0 and dP low to 0, this equation simplifies right down to the Gibbs-Duhem equation. Ni dd equals 0.
Okay. And for a simple binary system?
For a binary system, just components A and B, it becomes NAD plus NBD equals 0. You can rearrange that to DB NABD.
What does that tell us physically?
It clearly shows that at constant T and P, the chemical potentials of the components in a mixture can't all change independently. If one chemical potential changes, the others must adjust in a compensatory way to satisfy this equation.
So they're linked.
It's a powerful statement about the interdependence of these intensive properties in a thermodynamic system at equilibrium.
So it's not enough to know how much of each component we have. Their chemical tendencies to change are linked. That interdependence is a key insight. Okay, next up, we delve into deriving expressions for chemical potential in terms of other important thermodynamic potentials like internal energy U, enthalpy H, and Helmholtz free energy F. Our notes start with the general differential of I.
Right. We can express the total differential of I, which is a function of
T, P, and all the NJs is J on DTP plus DAGP, EDP, and JDP plus D. It looks a bit messy, but...
Yeah, lots of partials.
But we can relate those first two partial derivatives to other thermodynamic properties using the definition AGTP and J.
Okay, how?
We use the fact that for state functions, the order of differentiation doesn't matter. This is the basis of Maxwell relations, so we're not explicitly deriving those here.
Okay.
So IDP and J is the same as GPB, and we can swap the order.
We know is Knight and S, the total entropy, from DGG equals Knight SDT plus VdP plus Sendi S, nice C, where C is the partial molar entropy of component A's.
Partial molar entropy, okay.
Similarly, NaHe, NJ, and Jane is V, the total volume. So ATNJ, the partial molar volume of component B.
Partial molar volume.
Substituting these back into the differential for Dine gives us DAS6 plus VdP plus DA AAT PAAJ.
That looks a bit cleaner.
It relates changes in S directly to changes in TAT via partial molar entropy and volume. The notes also remind us that at constant T and P, DGTP equals sunny knee, and this represents the maximum non-expansion work.
Non-PV work, okay. And then we move on to see how I can be expressed as a partial derivative of U, H, and F. Can you outline those derivations? Highlighting the conditions, maybe?
Sure. Let's start with internal energy U. Its fundamental differential is du TdS PdV plus dN.
Got it.
Now imagine a process where we hold entropy S and volume V constant. So ds dV equals Sep.
Okay, constant S and B.
Then the equation simplifies to just du I. If we only change ni, then du equals idni. Rearranging this, we see that IU holding SV and all other NJ constant
So I is the change in U per mole of I added at constant S and V.
Exactly. Now for enthalpy H, remember, HU plus PV, its differential is DH, DU plus PDV plus VDP. Substituting DU gives DH to DS plus VDP plus EdNE.
Okay.
This time, let's hold entropy S and pressure P constant. So DS equals 0, DP equals 0.
Constant S and V.
Then DH simplifies to DH will N EdNE. Again, if we only change NE, we get I holding SP and other NJ constant.
Change in S per mole of I added at constant S and P.
You got it. Finally, Helmholtz free energy F, defined as FUTS. Its differential is DS DS. It's DS DU TS SDT. Substituting DU gives DF S SDT PDV plus EdNE.
Okay.
Now, what variables should we hold constant? Look at the equation.
We want to isolate the EdNE term, so we need DT0 and DFEO, constant T and D.
Perfect. If we hold volume V and temperature T constant, then DF equals EdNE. And so EdNE holding V and other NJ constant.
Change in F per mole of I added at constant V and T.
Precisely. These different expressions really show the versatility of I. It connects composition changes to changes in all the major thermodynamic potentials, just under different sets of constant conditions.
That's a really powerful way to see it. Okay, let's shift gears slightly and move to a cornerstone of thermodynamics. Ideal gas mixtures. How does the chemical potential of a component in an ideal gas mixture behave mathematically?
Right, ideal gases. The key simplifying assumption here is no intermolecular interactions.
No forces between molecules.
Exactly. This lets us treat each component as if it's behaving independently, like it occupies the entire volume all by itself.
Dalton's law territory.
Kind of, yeah.
Yeah.
The partial pressure pi of component I is related to the total pressure P and its mole fraction pi ITP.
Okay.
Now, for a closed system at constant temperature, the Gibbs free energy change is dG equal VDP. If we consider just 1 mole of an ideal gas, its molar volume V is RTP. So the change in molar Gibbs free energy, which is just the change in chemical potential DI, is dV bu PdP.
D equals RTP dP.
Right. Now, to find the chemical potential at some partial pressure pi, we integrate this expression. Let's integrate from some reference pressure pi up to pi at constant T.
Okay, integrate day from I at a day and integrate RTP dP from pi to pi.
Exactly. D gives IRT pi, IRT. The other side gives IRT 1 PdP from pi to pi, which is RTLN pi pi.
So ITP equals RTLN pi pi.
Correct. Now, if we choose our reference state, IRT, to be the chemical potential of pure component I at temperature T and some standard pressure pi, often 1 bar.
Just standard state.
Then we can write IT pi plus RTLN pi p. Now substitute pi IT.
Okay, ITP plus RTLN pi p.
Right. We can use log rules to split that logarithm, ITPP plus RTLN PP plus RTLN T.
Oh, okay.
Now look at the first two terms, IIR plus RTLN PP. That's just the chemical potential of pure I at temperature T and the total pressure P of the mixture. Let's call that ID.
Bu star I, the pure component at TNP.
Exactly. So the chemical potential of component in the ideal mixture becomes beautifully simple. ITP key plus RTLN she.
Mu equals mu star plus RT log mole fraction.
That's the one. It shows that simple logarithmic dependence on the mole fraction for ideal mixtures. The notes also mention you can use different reference states, leading to expressions like I1, I2 plus RTLN C2, C1, or involving mole fractions, but they just reflect shifts in that reference point.
That logarithmic term involving the mole fraction seems to be a key signature of ideal mixing. And from this expression for the chemical potential in an ideal mixture, we can derive the Gibbs free energy of mixing at mxg. How does that go?
Right, mxg. It's defined as the difference between the Gibbs free energy of the ideal mixture after mixing and the sum of the Gibbs free energies of the pure components before mixing, all at the same T and P.
G final minus G initial.
Essentially, yes. For the mixture, the total G is G N Li I. Using our new expression for I, that's G Ln I plus RTLN I. Before mixing, we just had the pure components separated. Their total Gibbs free energy was G equal Isa.
Just the sum of the pure component G's.
Right. So the change upon mixing is A mix G, GE equals plus RTLN GEI.
Their own EI terms cancel.
They do indeed. Leaving A mix G equals and RTL Vina.
Delta G mix is sum of Ni RD log Xi.
Or if you factor out RT and use Ni, where N is total moles, you get U mix G NRT EEA.
RET sum of Chi log Xi.
That's the standard form. And think about it. Moldy fractions Xi are always between 0 and 1.
So E ln E is always negative.
Always negative, which means E mix G for ideal mixing of gases at constant T and P is always negative.
Mixing is spontaneous.
driven by that decrease in Gibbs free energy, matches our intuition.
It does. Now, how do we find the entropy and enthalpy changes associated with this ideal mixing process? Me mixes and E-mix.
Okay, we use the relationship M-mix, E-mix edge. We also know the thermodynamic relation of RTTK.
Okay.
Applying this derivative relationship to the Gibbs energy of mixing. A-mix.
Take the temperature derivative of N-Celsius.
Exactly. The only T dependence is in that explicit T term. So the derivative is N-Celsius. And the negative sign out front gives the Yermix N-Celsius.
Delta S mix is minus NR sum chi log chi. Since log chi is negative, delta S mix is positive.
Always positive, which makes sense. Mixing increases disorder, increases entropy.
Right. So if MXG N-Celsius and N-Celsius, what does that tell us about MX from MX to MX?
Substitute them in. N-Celsius, MXT, N-Celsius.
So N-Celsius MX plus N-Celsius.
Which means?
MX must be 0.
Exactly. For ideal gas mixing, the enthalpy of mixing is 0. No heat is exchanged with the surroundings when ideal gases mix at constant temperature and pressure.
The spontaneity is purely driven by the entropy increase.
Alloentropic.
No enthalpy change upon ideal mixing. That's a key characteristic. And what about the volume and Helmholtz free energy changes during ideal mixing? A Vmix and an mix?
For ideal mixing, we assume volumes are simply additive. The total volume of the mixture is just the sum of the volumes the pure components would occupy at the same T and P.
So no change in total volume when they mix.
Correct. Fmx equals 0.
Okay. And Helmholtz Amix.
Remember the relation arrow A mix B A EV. So A mix A AE and mix V, since we're at constant P and AB mix 0, the OB EV term is 0.
So MXE Emix.
For ideal gas mixing, yes. A mix E and air 10 Shilanchi.
Can we get that from EFE?
We can. For ideal gases, internal energy depends only on temperature. Since mixing happens at constant T, and Mx equals 0, which equals Mxu plus P mix V, and AV mix 0, so Mxu is 0.
Right, so Mx A, E mix AE heresy, Mx E mix EBA, Mx V 0. And mixing is driven purely by A mixes being positive.
A neat summary of ideal mixing.
Now, let's step into the real world, or closer to it, with real solutions where interactions do matter. Our notes introduce Raoult's law here. What's the fundamental idea and its basis in chemical potential?
Raoult's law describes the vapor pressure of a component above an ideal solution. It states that the partial pressure PA of component A above the solution is equal to its mole fraction in the liquid phase, XA, multiplied by the vapor pressure of pure A at the same temperature, PA. So PA equals XA PA.
Okay, partial pressure equals mole fraction times pure vapor pressure.
Yeah.
How does chemical potential explain this?
It comes down to equilibrium. At equilibrium, the chemical potential of component A in the liquid phase must equal its chemical potential in the vapor phase. A liquid, A vapor.
Makes sense.
Now, for an ideal solution, we assume the chemical potential in the liquid is A liquid plus RTLN XA, where AL is the chemical potential of pure liquid A.
Like the ideal gas mixture form, but for liquid.
Exactly. And if we assume the vapor above is an ideal gas, then A vapor plus RTLN PP, where PA is the partial pressure of A above the solution, and P is some standard pressure.
Yeah,
So
well,
at equilibrium, AL plus RTLN hexa plus RTLN PP.
Right, now what?
We also know that for pure A at equilibrium with its vapor, at pressure PA, we have AL plus RTLN PPA.
Substitute that in for AL.
Substitute it in. AG plus RTLN PPA plus RTLN PP plus RTLN PPL plus
Right.
RTLN PP.
The G terms cancel.
They do. Leaving RTLN PPL plus RTLN PAO divide by RTLN PAP.
Let's go.
NLN AP plus LNXA.
Combine the logs on the left.
Right.
LNXA PAP.
Which means XA PA P equal is PA.
Cancel P, and you get PA equal is XA PA wall.
Wow. It falls right out of the equality of chemical potentials, assuming an ideal solution and ideal vapor.
Precisely. The law arises from equilibrium and the assumed forms for chemical potential in an ideal solution. That connection really clarifies the basis. Now, real solutions often deviate from this ideal behavior, right? Especially when the solute is very dilute. That's where Henry's law comes in, according to our notes. How does it differ?
Right. Henry's law takes over for the solute, let's call it B, when it's in a very dilute solution as its mole fraction XB approaches 0. It states that the partial pressure of the solute gas above the solution, PB, is proportional to its mole fraction in the solution. PB equals KHBXB.
Proportional. But the constant isn't the pure vapor pressure PB.
No, it's KHHB, the Henry's law constant for that specific solute B in that specific solvent A at that temperature. It's an empirically determined value.
Why the different constant?
It reflects the reality of molecular interactions. In a dilute solution, a solute molecule B is mostly surrounded by solvent molecules A. Its environment, and thus its escaping tendency, vapor pressure, is dominated by AB interactions, which are generally different from the BB interactions in pure liquid B.
The environment matters.
Exactly. Raoult's law, PA equals XAPA, tends to hold well for the solvent A when the solution is dilute, because as XA approaches 1, the solvent is mostly surrounded by other solvent molecules, like in the pure liquid. But for the solid B, surrounded by A, Henry's law, PB equals KHB XB, is needed.
So Raoult's for the solvent, almost pure. Henry for the solute, very dilute. The constants PA and KHB reflect the different molecular environments. A surrounded by A versus B surrounded by A.
You've nailed it. Deviations from ideality, captured by Henry's law, arise from these different intermolecular forces.
Got it. Now, our notes then discuss how chemical potential is fundamentally linked to colligative properties.
Yeah.
Those fascinating properties of solutions that depend only on the number of solute particles, not their identity.
Yes, the lowering of the solvent's chemical potential upon adding a non-volatile solute is the root cause of all colligative properties.
How so?
Remember, for the solvent A in the solution, its chemical potential is A equals A plus RTL XA. Since XA is always less than 1 when a solute is present, ln XA is negative. So A is always lower than A, the chemical potential of the pure solvent.
Adding solute lowers the solvent's chemical potential.
Always. And this lowering affects the phase equilibria of the solvent. It changes the conditions, like temperature or pressure, where the solvent's chemical potential in the solution equals its chemical potential in another phase, solid or gas.
Which leads to
the 4 main colligative properties. Relative lowering of vapor pressure, boiling point elevation, freezing point depression, and osmotic pressure. All of them can be quantitatively derived by setting the lowered chemical potential of the solvent in the solution equal to the chemical potential of the pure solvent in the other phase, vapor, solid, or pure liquid across a membrane, and seeing how T or P has to change to maintain that equality.
And the graph in our notes showing chemical potential versus temperature illustrates this visually.
Exactly. It shows the chemical potential curves for solid, liquid, and gas phases. Adding a solute lowers the liquid curve. This shifts the intersection point with the gas curve, boiling point, to a higher temperature, and the intersection point with the solid curve, freezing point, to a lower temperature.
Very clear. And that brings us to the derivation of 2 very important equations governing phase equilibria. The Clausius-Clapeyron equation and the Gibbs-Helmholtz equations. Let's start with Clausius-Clapeyron, relating vapor pressure and temperature. Can you walk us through its derivation?
Sure. The Clausius-Clapeyron equation in one common form is 1p dp dt. It tells us how vapor pressure changes with temperature based on the molar enthalpy of vaporization at rep.
Okay, where does it come from?
It starts from the condition for phase equilibrium between liquid and vapor. Their molar Gibbs free energies, chemical potentials, must be equal. Liquid, vapor.
Equilibrium condition again.
Always. Now consider a small change in T and P along the equilibrium curve. The changes in chemical potential must remain equal. Diliquid equals the vapor.
We know the general form ds SMDT plus VMDP, where EM is molar entropy and VM is molar volume. So EF, liquid DT plus VM, liquid DP equals ESM, vapor DT plus VM, vapor dP.
Applying differential form to both sides.
Exactly. Now rearrange to solve for dP dt, the slope of the coexistence curve.
Okay, group the dt terms and dP terms. VM, vapor VM, liquid dP, SM, vapor SM, liquid dt.
Right, so dP dt, SM, vapor dm, liquid VM, vapor VM, liquid.
dP dt is SFEP.
That's the Clapeyron equation. It's exact, no approximations yet.
Okay, so how do we get to Clausius-Clapeyron?
We introduce approximations specifically for liquid-vapor equilibrium, especially away from the critical point. First, the volume of the liquid is usually way smaller than the volume of the vapor. VM, liquid VM, vapor.
Vap, VM, vapor.
Approximately, yes. Second, we treat the vapor as an ideal gas, so VM, vapor, ERTP.
Okay, substitute RTP for IVVAP.
And third, we know that at a phase transition, the entropy change is related to the enthalpy change, AS-VAP-T.
Right, definition of entropy change at equilibrium. Substitute these into the Clapeyron equation. dP dt, each VAP T.
dP dt.
EPDT, VAP.
Exactly. Just rearrange that slightly by dividing by P, and you get the Clausius-Clapeyron equation, 1P dP dt, HAFAP RTT.
There it is. And the notes show the integrated form too.
Yeah, if you assume each HAFAP is constant over the temperature range, you can integrate it to get ln PdP1, 1T1, 1T2. Very useful for estimating vapor pressures.
So combining phase equilibrium with ideal gas and volume approximations gives us a powerful tool. Now, What about the Gibbs-Helmholtz equation? What does it relate and how is it derived?
The Gibbs-Helmholtz equation relates a change in Gibbs free energy, G, with temperature T at constant pressure, to the enthalpy H. The equation is GTP equals HTT.
Okay, derivative of GT with respect to T equals minus H over T squared. How do we get that?
This one often trips people up, but let's try the cleanest way from the notes. Start with the definition G equals HTS.
G equals H minus TS.
We want the derivative of GT. Let's first find an expression for S. Rearranging gives SHGT.
Okay, S, H, G, and T. Now, we also know the thermodynamic relation. GHTP is my F.
Right, from dg/sdt plus VdP.
Exactly. So substitute our expression for S into this derivative, GHT.
Okay, partial T equals GHT.
Now, let's actually calculate the derivative we want. GDTP, use the quotient rule for differentiation.
Okay, derivative of GT is T, GTP, T.
Correct. And a GT is just one, so it's TG, GT.
Now substitute our expression for GHT.
All right, substitute GHT for you to T.
It's not T cancel the first term, GH.
GTG. And
GHG is just H.
so we get HTT.
Exactly. GTP equals minus HT. That's the Gibbs-Helmholtz equation.
Phew, got there. It connects the temperature dependence of GT directly to H. And the notes give integrated forms too.
Yes, like GDT2 G1T1 JT, or if H is constant, G1T1 is H1T2 and T1.
Yeah.
Very useful for finding G at one temperature if you know it at another, and you know H. It's fascinating how these fundamental thermodynamic quantities are so tightly interconnected through these mathematical relationships. Now, our notes conclude by revisiting colligative properties and showing how their formulas can be derived directly from the chemical potential of the solvent in a mixture. Let's take one example, say boiling point elevation. Can you outline that derivation using chemical potential?
Certainly. Boiling point elevation, APPV, is how much the boiling point of a solvent increases when you add a non-volatile solute. We want to derive EPB equals KBM, where APM is molality, and KB is the abelioscopic constant.
Okay, start with chemical potential.
At the boiling point TB of the solution, the chemical potential of the solvent A in the liquid phase must equal its chemical potential in the pure gas phase. ALTB equals AGTB.
Right.
For the solvent in the solution, ALTB equals ALTB plus RTBlnXA. Here, ALLTB is the chemical potential of pure liquid A at TB, and XA is its mole fraction.
Okay.
So ALTB plus RTBlnXA equals AGTB.
Now what? We need to relate this to the pure solvent boiling point TB.
Exactly. At the pure solvent boiling point, TB. We know ALTB equals AGTB. We need to relate the chemical potentials at TB and TB. This is where Gibbs-Helmholtz comes in, or rather its implication for how changes with T.
Oh, relating the change to enthalpy.
Right. The difference AGTB, ALTB can be related to AHVAP over the temperature interval AITB equals TBTB. Also, the term RTBL and XA needs simplification. For dilute solutions, lnXA equals lnXNMA1XB.
Okay, lnXA is approximate XXB.
And for dilute solutions, the mole fraction of solute XB is approximately proportional to the molality MXB MMA1000, where Ma is the molar mass of the solvent.
So lnXA AED MMA 1000.
Putting these pieces together, relating the difference in terms to HVAP and XMA, and using the approximation for lnXA requires careful application of the Gibbs-Helmholtz equation or related thermodynamic integration. The result, after some algebra and assuming UB is small, is ATB Alifi HVAP ATA 1000 meter.
And that whole first term is just a constant for a given solvent.
Exactly. That's a abelioscopic constant KB. So we arrive at ATB KBM.
Fantastic. And similar derivations work for the other colligative properties.
Yes, using the same starting point, the lowered chemical potential A equals A plus RTLNXA, and applying it to the relevant phase equilibrium. Liquid vapor for vapor pressure lowering, liquid solid for freezing point depression, liquid across a membrane for osmotic pressure. Along with similar approximations for dilute solutions, you can derive all the standard colligative property formulas, APPAA, XB, AAAF, KFM, and ATOT.
It's truly remarkable how these seemingly disparate phenomena, boiling point changes, vapor pressure lowering, freezing point lowering, osmotic pressure, all stem from that same underlying principle, the chemical potential of the solvent being lowered by the presence of a solute.
It really underscores the unifying power of chemical potential.
It really highlights the power and elegance of thermodynamics in explaining the behavior of matter through mathematics.
Absolutely. We've journeyed through quite a bit: definitions, D and H coordinates, the maths of homogeneous functions, and Euler's theorem leading to a And then using Ointh to understand phase equilibria, mixing colligative properties via equations like Clausius-Clapeyron and Gibbs-Helmholtz, it's a testament to the deep interconnectedness of these concepts.
It's definitely much more than just, a collection of formulas. It's a coherent mathematical framework. It allows us to predict and understand the macroscopic world from fundamental principles.
I love it.
As we wrap up this incredibly deep dive, it does make you think about the assumptions we've made, doesn't it? Particularly the idealizations, ideal gas, ideal solution.
Crucial assumptions.
When do these models start to break down significantly in real-world systems? That might be a fascinating avenue for a future exploration, perhaps.
Definitely scope for more there. Non-ideal systems add layers of complexity.
For now, though, we hope this detailed look into the mathematical underpinnings of thermodynamics has given you a much more rigorous appreciation for the subject. As always, we encourage you to ponder these concepts further.
And let us know any questions or insights you have.
Thanks for diving deep with us.